Hello, welcome back to my channel, JBTeguihanon, your engineering and chemistry tutorial. So let's jump into our course, refrigeration system, but our topic is solving the problem, relating to various qualities or properties, of the substance called water. So here's the problem. This is the continuation of my my previous video. So here's a problem, the frictionless piston shown in the figure. This is the figure. Okay, has a mass of 16 kilogram. Heat is added until the temperature reaches 400 degrees Celsius. If the initial quality is 20%, A, or find A, the initial pressure. We have done that in the previous video. And B, find the mass of the water. So tonight we're going to study and continue the calculation of C, the quality when the piston hits the stops. And then also we find D, the final pressure, and also we will find E, the work done on the piston. So here's the figure. This is the piston. Of course, piston is under the piston you have water here, and the diameter of the cylinder is this one, and the height is this one. Okay, and you will add heat here at the bottom of your cylinder. So the fire or heat is added here. Okay, so that's the setup or the scenario. Okay, let's continue. So in here I have included the steam table for your information only. I believe when you study this type of the problem, this is just a review in refrigeration. This is actually the student had gone through this in a subject called thermodynamics. So assuming that you have all done your thermodynamics, so this is the steam table of the water, and we are going to collect the properties. What properties? The specific volume that I have encircled here, and this is table pressure table, right? So our pressure is this. Okay, we have calculated the pressure, which is actually 120 kilopascal, and this is it. This is in megapascal, so it's 0.12, okay, MPa. And here's the property or corresponding property in terms of Vf and Vg. Okay, so I'm going to remind everyone that we have this pressure. I'm going to write here inside the table. We have a pressure specific volume diagram. Okay, and you are gonna have a property graph like this, right? And this is your critical point on top. This is CP, critical point. And then I'm going to change the color. And you have a pressure line here, constant pressure line. Okay? And in this area here, this is what we call the the saturation liquid line. And this line here is your saturation vapor line. And actually this is the location. In here is your specific volume at vapor, saturated vapor, and this is actually your volume or specific volume at saturated liquid. Here is the vapor region, VR, okay, and this is your liquid region, in this region, right, LR. Okay, and this is what you call in here, we call it the critical pressure, PC. Okay, so that's the review, and this guy here is actually your okay, this guy is expressed in X, right? VG minus VF. Sorry, VF. Sorry. I'm going to erase it. Okay, and this is specific volume of liquid, right? And this is your what do you call that, percent quality, okay, in percent. Okay, so this is just a review, and let's move on to the next slide. So in the last video we have A. Our answer for A, I'm going to write down our P1 is equal to 120 kilopascal. Okay, as a recap, in the previous video, that's the answer. And then we have expressed the specific volume at 1 is equal to specific volume of the liquid plus the quality, and then the specific volume of vapor minus specific volume of liquid. Yeah, right. And eventually we have used the table, okay, the value of the table on the table, and this is 0.001 plus, of course, that's given, that's 20% or 0.2 times 1.428, right, minus 0.001. okay, and you're gonna have 0.286, right, and the unit is cubic meter per kilogram. Why kilogram? Because that is specific volume. So that was the answer in the previous video for the V, and then you are going to multiply or sorry, you have to, we've been asked to find for the mass, right? Then your mass is equal to volume 1 over specific volume 1, right? And then yeah, and the volume is equal, of course, to pi. That's the area of the cylinder, 0.1 square over 4 times the 0.05. Okay, and over 0.286 is 2, and you're gonna have point 0.00137, right? And that is in kilogram. Okay, that was what we got in the last, or in the previous video. Okay, so in here is the 0.5, the initial, in the figure you have the initial, height, right? Which is this one. But after it stops here, you have a stopper. Your piston will be in this. Okay. And your total high will be, this guy here, that is actually 50 plus 30, and that's gonna be 80, right? 80. So I cannot write it down because it's on the edge. I cannot erase it likewise, so I have to move it here a little bit here inside. Okay, it's gonna be 80 mm, because 30 plus 50 is 80. So yeah, when we calculate this mass, we account that, right? We account this one, we account this, right? Because we need to get the volume. This is area and this is the height, so area times height is volume divided by specific weight. Then we have the mass, right? We have got the mass, 0.00137 kilogram. Okay, so it's a little bit, yeah. So we continue. So how do we get C? C is C, we're gonna solve C. C is equal to, so what is he's asking, when the piston just hits the stops, the pressure is still 120 kilogram, okay? Sorry, kilopascal, and the specific volume increases. Okay, your specific volume increases, okay, and that is V2 over M, and that is equal to pi, area, right, 0.1 square over 4. So you have to multiply it with 0.8 now, okay, 0.08 rather, over the specific volume 1, which is 1 is 1373. Okay, and that is actually equal to 0.4458 cubic meter per kilogram. Okay, why per kilogram? Because we have expressed this in kilogram, volume per kilogram. Okay, and that is just a specific volume. So now the quality is then found as follows, using entries at 120 degrees Celsius. Okay, we are going to have this. Okay, 0.458, that's specific volume. 2 is equal to 0.001, that's the specific volume of liquid, plus x2, this is what we are going to find, times quantity specific volume of vapor, 1.428, right, minus 0.001. okay, then you have x2 is equal to what, 0.320, or that's going to be equal to 32%. Okay, that's the answer. That is the answer. Okay, when the cylinder stops, okay, you are going to have quality. When it stop here, this figure here, this is where the cylinder stop here. Okay, your specific your x there is 32%, right? Quality, initially it's just 20% in here, right? But as you add heat here, this piston moves up, right, because of the pressure exerted by the water vapor up to this point, right, up to this point here. Then the percent of your water increases, so it's becoming more vapor, so it's become stronger. Okay, so going back, continue. What's the time? So it's 11 minutes or 18 minutes already. So D, so we have asked to solve for the final pressure. The final pressure, it's quite difficult to compute, right? It's difficult to compute. Okay, what we're gonna do is, after the piston has stops or hits the stopper, the specific volume actually ceases to change. There is no more change of the specific volume. Remember, what changes there is specific volume, right? Okay, and it remains constant. So using temperature 3, so we are now solving D here. Okay, we're solving D, and then we use temperature 3, and that is actually given 400 degree Celsius. And of course, we're gonna use also the specific volume 3. That is actually 0.458, right? And then we're gonna interpolate it. No, we will be using table, okay, wherein you have the this is actually a superheated vapor table, wherein we use the pressure, okay, the pressure between 0.6 megapascal and MPa, and also and what point, sorry, 0.6 here, and 0.8, 0.6 and 0.8, both of course megapascal, so that you can solve the of course this is at a temperature of 400 degrees Celsius. Okay, so by interpolation, P3 is equal to, substitute now the value. So from the table, I'm not going to show the table because I have shown it already. This is just a review. So plug in the value from the table. Okay, what table? Superheated table. 0.4, this is 458, right? And then over point, this is same value, 5137. This is 7 minus this another value here, 3848. Okay, quantity. Then you have your 0.8 minus 0.6 plus 6 plus 0.6. P3 therefore is equal to 0.686 megapascal. This is your final pressure. Okay, when the cylinder stops at the stopper, this is the pressure, final pressure. Let's move on as our time is getting longer. So at E, we have been asked to solve for the work. So remember that there is a zero work done on the piston after it hits the stop. No more work. So from the initial state until the piston hits the stopper, the pressure is constant, right? Because this is constant pressure. So our work is actually equal to pressure times volume, or change of volume. But we don't have volume on the table, right? Stem table, so we express it with specific volume 2 minus specific volume 1. Of course, you have a mass times mass. Specific volume times mass is volume, right? So yeah, what we have is 120, that is the pressure, and then we have the specific volume 4.458, right, minus 0.286, right, times mass, which is right, which is just a presentation to make it volume. No, not presentation rather, but you have mass, right? 0.0013 73. I think I've forgotten to write down the 1 there. It's 1373. So your unit will be in kilojoule, right? 0.0283 kilojoule, or this is 28.3 joule. Okay, this is the final answer. Okay, thank you very much. I hope you got it. Thanks for watching. It's 25 minutes, so it's quite long. Thanks for watching. Please subscribe to my channel, JBTeguihanon, your engineering and chemistry tutorial. Thanks. God bless for now. Bye.